Well, welcome back everyone so far. We're just going to run the clock and get started in less than a minute. Over there, folks. Looks like we're going to close out week 7 now. For our last topics on Thursday today, we're going to be looking into a characterization theorem. It's a pretty big word, but any characterization theorem in mathematics is essentially just a theorem that's trying to say what are all the ways, all the concepts, all the possible things that you can connect with the concept of invertibility. So we'll be looking through this characterization theorem. Possibly, I know this was for the same for me. In your program of study in mathematics, this is possibly your very first characterization theorem. There's many, many more. The more algebra, the more analysis you take, these things start to show up a lot. So this one feels imposing at first, but it's just a natural way to give a big summary. What does invertibility mean, connecting through all the other terminologies we've seen so far in linear algebra? Then, after we work through a couple examples in this section, it's actually kind of a short section relative to the other ones we've seen in chapter 2. We'll go off to section 3.1. We'll probably make a little bit of progress, not going too far, on introduction to determinants. We'll be looking more on the algebraic side of determinants, just the computational machinery of how do you crank out a determinant given any square matrix, size 2 by 2 and higher. But if you want to look into the geometry, there's a reading at the very end of this document and a really excellent video by, once again, the 3 Blue, 1 Brown series of YouTube videos showing excellent animations on what the geometry of a determinant really looks like. So that'll be our plan for today. Also, the next big announcement, of course, is that our exam 2 is going to be next Tuesday. That means for the in-person section, we'll just be here quietly working for the 75 minutes or whenever you finish the exam. For the online section, I sent out the instructions and a reminder for scheduling your exam. If you're all squared away, then we won't have class on Tuesday. That'll just be all we're doing on that particular day. If you have any questions about scheduling your exam, if that link that I sent through the inbox here gets lost or just doesn't seem to show up at all, let me know right away and I'll connect with you on the instructions on scheduling the exam. Well, any questions at the moment, folks, about any of those announcements? Okay, well, really, like we mentioned before, really the number one way you can get prepared for this exam is being caught up on the homework. So if you even got behind on a single section or a couple, I'd say make that your number one thing to do to prepare for the exam. I do accept homework sections that go late for full credit. Essentially, these due dates are really more about pacing than anything. So if I don't get your assignment section 2.1 today, I put a 0 in the grade book and your course grade inside here gets reflected. But if you get that to me sometime this weekend, then your grade gets modified. I don't penalize on these because this is the best way to learn the homework is doing the material, and it's the best way to prepare for the exams. Also, as far as the grading goes, I'm going to be watching my email quite a lot this weekend and try to stay as caught up on the grading as possible. I should be sending you the graded section 2.1 back on Friday, probably in the afternoon. And anything that you send me, if it comes in late, even on a Sunday, even potentially on a Monday, I'll make every effort to get it graded and sent back to you before Tuesday. But really what we've got going on is just a kind of a total repeat of the routine that we saw going into exam 1. So take a look into the same related documents as you study for the exam. Make sure you have this formula sheet pulled up as well so you know what'll be available, where all the information is. And it's not going to be any too different. It's going to be about the same number of questions, plus or minus about one single question, and the same nature of the questions. Some of them are computational, like writing down a solution set in parametric vector form. Others are purely just conceptual questions, like what is the domain, what is the codomain, and that kind of stuff. But I think that's my entire spiel for announcements that relate to the exam. Any last questions or comments before we jump into this section? Okay, well, let's get started. Section 2.3 is a pretty cool section because it being a characterization theorem, it really reviews the entire course up to section 2.2. A lot of our terminologies, methods, and ideas are all just collected in this theorem. So here's what it looks like. We've peeked at it before. It's a gigantic looking theorem with parts A through N that grows as we get into chapter 3, into chapter 4, and even more in chapter 5. But there's a definite logic to it. First, we're talking about n by n matrices, which makes sense because that's the type of matrices we can invert. They have to be square. So part A is an invertible matrix. That's why it's called the invertible matrix theorem, or I'll use this acronym a lot. I'm not a fan of acronyms, but this is a good short up. Kind of like FTC would mean the fundamental theorem of calculus. So part A relates invertibility of a matrix with a whole lot of information. I highlighted two parts. Your access point into this theorem are the pivot positions, because usually that's something that's easy to reveal from a matrix. Row reduction does that. Sometimes even faster, depending on the matrix we're looking into. The determinant does just as good of a job. And so these are two great ways to get started working inside this theorem. Aside from that, let's do some organization with it because there's a lot going on. Let's color code these parts just to say what each part means. I think anything I color code in this purple or violet, whatever color that is to your eyes, this will be about invertibility. Anything in this color, let's say this one will be for, I think that was usually, well, it just depends on the section. Let's go with linear independence. And for this color, let's relate that to spanning. So the theorem is kind of broken up into these chunks. It's a little bit scrambled, unfortunately. I'm just writing it down verbatim as you see it in the textbook, so it's not extra confusing. As far as invertibility goes, it's definitely part A because that's just really the statements right there verbatim. We had a theorem in section 2.2 that A is invertible if and only if it's row equivalent to the n by n matrix. So this is a summary already of section 2.2. We use that as an algorithm to invert to 3 by 3. And then these parts down here, this is the definition of invertibility, that you can pre-multiply your matrix A and get the identity, or post-multiply the matrix A by some other matrix and get the identity. This is a strange theorem because really, taking both parts J and K together, the matrix C and the matrix D would be the same exact matrix. So our author wrote it in kind of a funny way, but in the most general way possible, without accessing other theorems that would say that has to be the same matrix. Well, that's also part L, just saying the transpose is invertible at the same exact time. And this is kind of a wrap up of section 2.2 when we first defined invertibility. Next, linear independence. We say a list of columns are linearly independent if and only if the matrix equation or the vector equation has only the trivial solution. So that's essentially the definition of linear independence. This is a restatement here. The columns form a linearly independent set. Again, parts D to E is the definition of independence. But what this is saying now so far is having n pivot positions. If this was 3 by 3, we're saying 3 pivot positions. Then you only have the trivial solution. The columns are linearly independent. And that's the same exact concept of the matrix A is invertible. So that's kind of cool in a way. Let's see what else we have. Independence is tied to with 1 to 1 at the same time. And I think that's about it for independence. The rest is spanning. Definitely, this is spanning. It says it right there. If you look into the theorem 4 we used in section 1.4, spanning also tells us the matrix equation here is always consistent. There's at least one solution. So spanning is really this concept as well. And we've related spanning to the linear transformation T being an onto mapping. So part I is really a statement about spanning at the same time. So this is the whole organization of the invertible matrix theorem. We'll add more concepts as we go. And our goal here in these notes is just to practice this, working with the theorem, seeing what it says in various different points of view. Well, any questions at all, folks? Just eyeballing the theorem pretty much is what we did. Okay, again, if I were to reorganize this, I'd put parts J, K, L up on top because that's really just about invertibility. But this is always kind of a great idea. Anytime you have a huge theorem like this, try to organize it somehow so that your brain can make sense of all these different statements. That way, it doesn't feel like just a whole bunch of gibberish. There's a relation how all this came together. It's telling us invertibility is the same thing as independence, is the same thing as spanning for square matrices. All of these statements will either be simultaneously true or they will be simultaneously false. And that's what example 1 is about. It says determine if the following matrices are invertible, justify your answer. And kind of the goal here is to use as few row operations as possible. In view of that, we could just take the determinant of A right away. Determinant of that matrix, say here, is going to be the product of the main diagonal, 9 times negative 20, so negative 180. The product of the off diagonal, 12 times 15. I don't have a calculator nearby, but watch out for the negative signs. That's going to be minus negative 12 times 15. Turns out that is actually negative 180. So this is negative 180 plus 180. This equals 0 directly. And so now part M of the invertible matrix theorem is false. Once this is shown to be false because we got it identically 0, everything here is false, including all the way on the top. We are wondering about invertibility. So now all we say is A is not invertible, or we could say it more briefly, A inverse does not exist. And if you like a good shorthand for the notes, because we're going to be writing this out a lot, you can just say A inverse DNE. That's something we say a lot in calculus when a limit doesn't exist, for example. And that's just a nice shorthand way to say it. I'll usually just write it out. It doesn't hurt. So that's the first one down, and we'll practice with several more just to get the feel for this. So next one on the list, let me zoom out just for a touch briefly on this one. Can't quite get to where I want to go, but that's as close as I can zoom out on that without causing trouble. On this matrix B, when you stare at this one, what would you say about this one? Is this one invertible or is it not invertible?
Not invertible.
Good call, absolutely. What would you say the dead giveaway is on this one that causes it to not be invertible?
The codomain is 4 while the domain is 3.
Yeah, absolutely. Viewing this as a mapping, invertibility, notice, requires the domain and codomain, like you say, to be identical. So already that's a problem all on its own. I think that's a great way to look at it. Thinking of it as a functional mapping, we require this for invertibility. Also, it just has to be a square matrix. So you could just say, since B is 4 by 3, B inverse does not exist. So that's the preamble statement on the invertible matrix theorem, but it's also right here as well, looking into these two different parts. So kind of a silly question, really, but it just is a reminder. Look before you leap. If the size of the matrix isn't square, then we don't have a concept of invertibility whatsoever on this thing. Now we have to scroll, leave the matrix behind, but presumably maybe you have a second screen or a printout of this. Sometimes I'm going to pull up this document right here, but it takes a lot of real estate as well. We'll pull it up when we need to. Well, let's leave it pulled up, actually. Here's our next matrix C. The key thing about this matrix is that it has a 0 row. But the moment that happens, it's a 3x3 matrix. So that would be n is 3 in this theorem. There's no possible way for us to get 3 pivots any longer the moment we have a 0 row or a 0 column. 0 column is tied together with linear independence. We'd be linearly dependent if there's a 0 column. Or you could relate this to columns. Just take the transpose of this matrix, C transpose. Now you have a zeroed out column. The columns would be linearly dependent. And that would mean C transpose is not an invertible matrix, which relates back to C as well. So there's a lot of different ways you can argue with this. There is A through M different approaches to look into this one. But the giveaway on this one is, I'd say the pivots. We can say here, C is 3x3. And has a maximum of 2 pivots due to the 0 row. So we're done on this one. This immediately tells us C inverse does not exist. So that 0 row caused the problem immediately. So maximum of 2 pivots there. At size 3x3, invertibility requires, keep clicking on the wrong one, we would have 3 pivots for that particular matrix. Well, that's 3 down. We haven't done row operations yet, so that's kind of a comfort in a certain sense. On this one, I probably would. It's a little bit harder to see unless you're really good at analyzing the columns and detecting if one column is a multiple of the other. Sometimes my zoom causes these numbers to be strangely readable. Let's zoom in a little bit more. So let's make this one a row operation problem. If you see a relationship among the columns, a dependence relation, that'd be another clever way to answer it. But we can just brute force crank this out. So let's take row 1, add it to row 3. We have 1, 5, negative 11, 0, 12, negative 3. Adding the rows is going to give us 0, 12, positive 3. So now it's 1, 5, negative 11. Let's multiply row 2 by negative 1, add to row 3. We'll then get 0, 0, positive 6. But this then exhibits 3 pivots altogether. So if we were looking for a linear dependence relation, there is none. It's probably just faster to row reduce in a lot of cases. At least for me, I can't do that many mental arithmetics on vectors just in my head. This is just a little bit faster of an approach. At this point, you could say, if there are 3 pivots, again, there's a lot of things you can say, but 3 pivots already tells us that matrix D is in fact row equivalent to the identity matrix. So some people might say that. They might just say row equivalent to I3. And then you can say, therefore, D inverse does exist. I'll just say exists briefly. Other people might just simply say there are 3 pivots. It's of size 3x3, so A inverse exists. So you can be as creative as you want to be on these, but oftentimes pivots and the determinant are a good go-to for methods. Well, that's our quick rundown on these. This exercise is kind of similar to when we were back in section 1.7, just listing out columns and determining which set of columns is linearly dependent. We tried to do it by looking into theorems and then did a whole set of them by visual inspection. In fact, that's such a strikingly similar problem. Let's take a look into that. Section 1.7 on linear independence first had a lot of theorems related to this concept. So we ran through them one by one. Then we looked into a list like this, and we were just thinking in terms of what theorems we have available and determined which ones were independent, which ones were dependent. This is the same kind of concept in a real sense. Put this in a matrix and the question can just change from, does A inverse exist? You're doing exactly the same kind of thing. So this is a pretty common question on exam 3, since this is now exam 3 material, just like this one is a pretty common question on an exam 2 setting. Going down below, here's a couple more related concepts. These ones feel more abstract because we don't have an actual concrete matrix we're looking at. We just have some information about the matrix. This one happens to be of size 6 by 6. We know something about the equation. Cx equals v is consistent for every vector v in R6. Checking the dimensions, yeah, x would have to have 6 rows for that multiplication to be compatible. And because it's square, the codomain is in R6. It asks, is it possible that for some vector v, the equation Cx equals v has more than one solution x? Why or why not? It's kind of a head scratcher, unless you're thinking about the invertible matrix theorem. It's saying the matrix equation is always consistent. You might be thinking in terms of theorem 4 in section 1.4. If you are, that's a great way to think about this one, because that could directly be a theorem you're accessed. But what we're asking is, yes or no, does Cx equal v have more than one solution x? That's a part of the invertible matrix theorem, potentially, or maybe not. Let's take a look into that. The idea here is we want to relate part of the information about the problem and see what we can do with the statement here, part of the conclusion. So Cx equals v is consistent. Let's take a look into this. That looks like part G, essentially. Part G says Ax equals b has at least one solution for every vector b in Rn. Well, that's more information when you say at least one solution. This says consistent. We're wondering, does that mean there's multiple solutions for some vector v, or exactly one solution for every vector v? But being consistent allows this to be true. There is now at least one solution for every vector. So we can say in the invertible matrix theorem, part G is true. So let's let that be our first part on this as we write it out. Since Cx equals v is always consistent, part G of the invertible matrix theorem, like we mentioned, this is going to be our pretty much go-to acronym right here for invertible matrix theorem. Part G of the invertible matrix theorem is true. All the other parts are logically equivalent, so you don't have to say each and every time. That means all the other parts are logically equivalent. We'll just take that as for granted. But now we wonder, is it possible Cx equals v has more than one solution? Going back to the theorem, there's nothing directly stating having more than one solution or a unique solution, but all these parts are true, and so in particular, that would mean this part is true. There are exactly n pivot positions, and n would be 6 in this problem, since it's a 6 by 6 matrix. So let's say something about the pivots. This is just one way to solve the problem. If you see another way, that's a great way to think about it. So I'll write here, this means C has n equals 6 pivot positions. Or in other words, forget which part that is, that's part C. Part C of the invertible matrix theorem is true. So if we have 6 pivot positions, and it's of size 6 by 6, we can say something about Cx equals v. Let's say down next, this means Cx equals v has no free variable. That's because every single column in the matrix C is a pivot column. There's 6 columns in total and 6 pivots. So automatically, there is no free variable. Let's connect that thought, though. Since every column is a pivot column. That deserves an exclamation because this resolves the question. we were asked, is it possible for some vector v, Cx equals v has more than one solution? And we can now say that's impossible. If there's no free variable, that means Cx equals v, it's always consistent, and it must have a unique solution now at this point. Free variables are what gives us infinitely many solutions. So we can now say, therefore, there being a pivot in every column, Cx equals v has a unique solution for all v in R6. So we answered the question of, is it possible? It was a direct question we were being asked. So if you feel like you didn't totally say it in their statement, you could start off by saying, no, it is not possible. And then clarify, this would be the conclusion. It's always a unique solution, no matter what. So that's kind of an interesting set of information. If your matrix is square and the equation is always consistent, there's in fact a unique solution for every vector v that you pulled out of R6. But if you thought in terms of pivots, again, that just means the columns are automatically linearly independent. The matrix C is invertible, so you can just directly solve this equation. In fact, that's what we did in section 2.2. The 2.2 approach would have been C inverse exists. Therefore, X equals C inverse times V. There's your unique solution. We can algebraically just exhibit it. So that's another creative way to think about this problem. And many other ways still, because there's just so many parts in the invertible matrix theorem. But any questions, folks, with this approach here? Okay, so this is what the invertible matrix theorem is all about, just making connections between the concepts. And it's a rich set of connections whenever your matrix is square. If you lose the fact that it's a square matrix, we have to resort all the way back to just one last call out, because it is an important theorem that's still useful for the rest of the semester. But if your matrix is not square, you're back in this land. I'm overloading this computer. I can hear the fans whirring up. This theorem is your only set of nice connections for the non-square matrices. So the moment the matrix is square, we get all of this stuff, which is pretty impressive. And also, notice what we found here. We have found that there is a unique solution for Cx equals V, the moment there is essentially at least one solution. So it makes you wonder, why not just change this and say right here, there it has exactly one solution? The reason for that is, in this characterization theorem, what we just proved is a bona fide theorem. We used the ideas here, connected them together, and our next theorem would be, there's in fact a unique solution. The author didn't want to overload this with a whole lot of additional theorems on top of it. So we just let the base concept, x equals b has at least one solution, is the base concept coming all the way from here. X equals b has a solution, or at least one solution. It could have been rewritten to. So that's a more abstract way to look into the invertible matrix theorem. Let's try it one more just for extra practice on this one. On this part, we have another n by n matrix, and that's always nice to see. That means we have the invertible matrix theorem working in the background. And it says now, if Hx equals C is inconsistent for some C in Rn, what can you say about Hx equals 0? So now the homogeneous equation, and why? Really the same kind of problem, just different set of information. The thought on this is, we go back to the invertible matrix theorem. Hx equals C is inconsistent. That's really something about spanning now. And that would be part G right here being false this time. Let's start off by just saying that. Part G of the invertible matrix theorem is false. Since Hx equals C is inconsistent for some C, not all, but there's some we can find in Rn, part G of the invertible matrix theorem is false. So now that we've said that, we have A through M different statements we can take a look into, minus part G. We just kind of used it up already by making that observation. But every single statement here is now false. The question said, what can you say about the equation hx equals 0? Anyone see which parts that would be related to on the vertible matrix theorem?
Would it be that it only has the trivial solution?
Yeah, we're now going to relate it to part D. This is a weird way it's been written, right? This is, I think, a problem written verbatim out of one of the potential homework exercises. What can you say about hx equals 0? We'll relate it to part D right here. Ax equals 0 has only the trivial solution, but since part G was false, this part is false as well. We'll say ax equals 0 has non-trivial solutions. And that would be what we can say about the equation here. So since part G is false, we can now say, or we might write, this means part, I already forgot what part that was, that is part D is false as well. And so hx set to the 0 vector has, well, part D said only the trivial solution. Now this means it has non-trivial solutions. We could have said a whole bunch more, but it was asking us directly just about the matrix equation here. So I think that'd be the response that we would have been going for on that kind of problem. We know a lot about this matrix H. The columns are linearly dependent. The columns do not span Rn, whatever n happened to be. Maybe it's 12 or 8. And really all these other statements as well, we can just put a false to and make a new comment. But we were directly asked about part D, so that's how we would end the problem here in this kind of way. Kind of a faster one. I think this one was tougher of the one above because it had more connections, but this was just directly connecting two parts of the vertible matrix theorem together and making that conclusion. There are several homework exercises that go kind of along these lines as well. If you get mixed up, if it's vague what the connection might be, don't hesitate to write about it. I'll be happy to help out. Some of these can be deceptively tricky sometimes, especially with the wording, because when it says, what can you say? It feels like it's a really wide open problem. So if you're not sure what the author is even asking, I can help reword what they're going for. Well, that's a couple look into their vertible matrix theorem from the point of view of computational problems, more just connecting the ideas together in examples 3 and 4, or excuse me, 2 and 3. For the next part, we want to look into this portion of the vertible matrix theorem, where we're dealing with the mapping. And if you have your book in front of you, or if you pre-read in this section, you have a really keen eye, you might have noticed that I reworded the parts of this. The author didn't say it this way, they said it this way. X maps to AX is 1-to-1. That's a perfectly fine way to say it, but I want to relate this directly to the transformation T, because those are the theorems that you're going to actually see written out. So I just rewrote this part in this way. Similarly, down below, this part was really written X maps to AX. It's fine notation. It does get used a good amount, but then the theorems don't use this as much. So again, I rewrote those two parts. So if you're wondering about the discrepancy, this is just my favorite notation, it turns out. I felt like that's vague when you're trying to connect it to theorems about a transformation T. It's good to just see T looking at you on the theorem itself. So now we're looking into transformations and how it's going to relate with the vertible matrix theorem. First is the concept of invertibility. And we looked into this a little bit before. This one is specifically for a linear transformation, and the definition of invertibility for that one versus the definition down here goes a little bit different. For transformation, we can say T is invertible if it's one-to-one and onto. It's weird having multiple definitions. So here's a second definition for invertibility. It's not that this is false. This still applies. In fact, it's part of the invertible matrix theorem. Here's the one-to-one part. Here's the onto part. So these two portions of the theorem are just directly imported from section 2.2 in this kind of way. I think we're done with that slide at that point. But here's a whole different way you could define invertibility. This is kind of nice in a way because it might remind you of material like pre-calculus 1, college algebra. Invertibility means that this transformation can be paired with another transformation S, or you might call it T inverse after you get past the definition, such that if you compose in this way, you get the vector X. And if you compose in this way, you get the vector X as well. Oftentimes we're very specific on the domain and codomain of that vector X, but the domain and the codomain is the same. So we just said for all X in Rn. And we'll write the inverse as T inverse in this kind of way. And down below is just meant to be a really fast concept problem, just churning through this notation. So a bit of a cognitive break. These are transformations as well, but not in the kinds that we typically think of, like these linear transformations. T mapping R into the set of positive numbers will be the exponential function. S mapping the positive numbers into the set R will be the natural logarithm. And we know from our training in algebra that those are a pair of inverse functions. And so the notations above would really just be saying this. S of T at X is S of T at X. That feels redundant, but this is now the name of the function on the inside, and this is the actual operation we take. This would be S of E to the X, which would be the natural logarithm of E to the X, which would be X itself, and this would be for all X in R, the domain of T. Here, we didn't have to be as precise because the domain and codomain were the same. To really have a pair of inverse functions, we have to reverse and compose them this way. This is absolutely required in college algebra type functions. So we would go T of S at X is equal to T of S at X. So now it's T of natural log of X, which means it's e to the power of natural log X. And that results in an X as well. But this doesn't work for all X in R. This only works for the values of X that's in the domain of the natural log function. So this is for all X in the set of positive real numbers, 0 to infinity. After you do that, you can just conclude S equals T inverse. So that's what this core definition is really all about. Invertibility means you can compose and get back the vector X in these two different kind of ways. Any questions with kind of that fast review topic here from days ago? Okay, there's a little bit more going on here because the moment you say the transformation T is linear in this definition, we have something available to us immediately. There is a new way to define T of X. T of X could be written as A times X for some n by n matrix A. So if we want to focus on invertibility as a function like this is a fine definition. But if we want to think about it as what it does with a standard matrix, this is our key into the invertible matrix theorem. This is an n by n matrix now. Then similarly with S of X would be equal to a matrix B times X for some n by n matrix B. And let's extend this down just a little bit. that would mean these equations, they really have a different kind of format. S of t of x is just like in our warm-up problem, still S composed of t composed of x, but t at x is just this matrix multiplication, a times x. This entire a times x is just a vector in Rn, like before. So it's playing the role of where that x would be when we use the mapping S of x. This turns into b times a times x. And this gives us an interesting, important way to think about matrix multiplication. Matrix multiplication can be viewed as just a composition of linear functions, just by this operation. So this is b times a at x. And that's, again, a pretty interesting view of what matrix multiplication is doing. Let's write this in as a comment. Matrix multiplication can be viewed as function or transformation. I'll go with just function composition. Then we can turn it around again, reverse the mapping. So we're doing t of s at x. T of s at x is now t of x at x. That sounds redundant, just saying it. But that means it's t of b times x. Then the b times x is an n by n vector. It can be placed right here when we do the transformation t. So back over here, this is now a times b times x. So this becomes ab times x, but t is invertible. S is the inverse. Both of these equal x. That means b times a is the identity mapping or matrix. It's equal to x. A times b is also the identity. So in equals x. And the vertible matrix theorem says something about this immediately. If you're getting the identity matrix like this, that means you found some matrix multiplied by a to get the identity, and that was the pre-multiplication. That's what happened right here. That's the pre-multiplication part. And you also have it working with the post-multiplication. D times A, well, that's the matrix B, giving us the identity matrix again. That tells us immediately he's an invertible matrix. So the moment you say T is invertible, this is a long form way to say, through this definition, therefore, A inverse exists. So invertibility of the linear transformation, this is the key that makes this all work. The fact that transformation is linear means the standard matrix is invertible. And same for this one, B. The inverse of B would just be the matrix A. We might as well say that just to throw it on there. B inverse exists as well. So next, we're going to just make use of that in an actual definite problem instead of the warm-up like we saw below. But any questions about these ideas so far? Our main goal is to connect this to these parts of the invertible matrix theorem, parts J and K. Don't know where to put that. Let's just minimize it. Okay, let's put this to practice then and actually compute out an inverse. Here's the write-up. Theorem 9 just kind of abbreviates all the thoughts that we put down on paper. Theorem 9 is essentially a consequence of the invertible matrix theorem and the definition for invertibility of a transformation. It says, let T be a linear transformation. It's going to go from Rn to Rn. And if those spaces differ, it's not invertible any longer because the standard matrix A is not square any longer. But it'll have a standard matrix for any such transformation. And the concept of T being invertible, this will happen if and only if A is an invertible matrix. So the moment you write T of x equals A times x, where did we ever write that? I don't think it's written down on paper here. let's make that be the concept here. If A is a standard matrix of T, just as a reminder, that means T of X equals A times X. Anytime you define a transformation like that, invertibility of A is the same concept as the invertibility of the transformation T. That means those equations will be satisfied, and we just compute T inverse by writing it as A inverse times X. That was the other part of our write-up that we were writing down in this color here, the additional comments. So let's try it out with this one right here. Here's a transformation going from R2 into R2. This looks like it ought to be linear. We can exhibit that halfway just by finding the standard matrix. And we'll explain why it's in fact invertible. First, let's write out what that standard matrix is. You could calculate T at E1, T at E2 if you like that approach. I think it's a little bit more algebraically rapid to just go T of X equals 6x1 minus 8x2. Then go to this is just row 2 written sideways. Negative 5x1 plus 7x2. That gives us the matrix immediately, 6, negative 5, negative 8, 7, multiplying by x1, x2. So this is the standard matrix A we just found, multiplying by the vector x. So explaining why the transformation T is invertible, this one right here, just boils down to why is the matrix A itself invertible? Loads of ways to do this one, but I think a favorite approach for 2 by 2 is calculating the determinant. It's pretty rapid most of the time. So let's compute determinant A. That would multiply the main diagonal, 6 times 7, minus the product of the off diagonal, negative 5 times negative 8, mind the negative signs. So this is 42 minus 40 for positive 2, which is not 0. And that's great. If we have not 0, that means A is an invertible matrix. Let's say that here. Therefore, A inverse exists, or we could say A is an invertible matrix. And so T inverse exists. So that's the concept here connected by the if and only if. If we said T is invertible, A would have to be invertible as well, but we computed and found A is invertible through this comment. So we went backwards through the logic and landed on T is invertible as a transformation. Well, next thing we'll do is find a formula for T inverse x1, x2. I put this in yellow since we're going to go for this as well in our homework exercise when we do this in section 2.3. If the notation is given in this way, I think it's a good skill to write the inverse in this exact format. And that would be a good practice anyway. If someone is giving you your mapping in this way, that's just their standard way of writing it. It's polite to just give it back in that same notation. But it's just an additional skill practicing the transformation in this way. Well, to find a formula, we know that T inverse is just A inverse times X. So this boils down to just computing A inverse. We already have half the work when we found that the determinant is 2. So now we can say A inverse is going to be, take the reciprocal of the determinant. We play kind of a number game on the matrix A up here. We swap main diagonal. So now it goes 7, 6. We multiply off diagonal by -1, so now it's going to go 5, 8. In this case, I would just multiply it by a half. I don't think it saves any time to leave the scalar out there. So this becomes 7 halves, or 3.5. 5 halves, 4 and 3. You know, it might be kind of cleaner to actually write it this way. 3.5, 2.5, 4, 3. So there's A inverse. Now to get the formula for T inverse, we can just write that T inverse, that's this part of the theorem here. T inverse at X is equal to A inverse times X which is going to be, let's scroll down, 3.5, 2.5, 4 and 3, multiplying the column vector, x1, x2, putting it in the same notation as above, just means we're going to write it comma separated. So 3.5 x1 plus 4 times x2, comma 2.5 times x1 plus 3x2. So this transformation here has the inverse written out in this way. There's definitely a formula to make that happen. That formula is tied together with the determinant, the inverse, and then cranking out this multiplication. So stages to getting to that point. Any questions at all, folks, writing all that out? Okay, well, this is the part where we're just about done. I was going to say we are done, but I forgot there's a couple more. Just a couple more looks at things that we can do with the invertible matrix theorem. But these are kind of fast summary type questions. We're still looking into these parts I, as well as parts F, where we're emphasizing the mappings, the transformations. And this is kind of a redo of content we saw all the way back in section, way back here in section 1.9. Let's pull that up. So 1.9, we had a nice summary theorem way down the line that told us what it means for mapping to be onto, for mapping to be one-to-one. It's just the concept of having a pivot in every row, a pivot in every column in the standard matrix. But now if you go from Rn to Rn, having a pivot in every row is the same exact concept of having a pivot in every column. And so that's why spanning and linear dependence become the same concept. So really, that's just what this theorem is all about. We have n pivot positions, so one-to-one means pivot in every column, as well as a pivot in every row simultaneously, all in the same time. So this one says, assume the transformation from R4 to R4 is onto, and the key to this one is that T is linear. To explain why T has to be now invertible mapping, well, let's take a look into the theorem. Nothing in the theorem directly takes T and say T inverse is invertible, but we can connect a couple ideas. We were told that this is an onto transformation. That's just immediately part I. So let's go ahead and say that right there. Maybe as well, the moment we know T is linear, let's also say, since T is linear, T of x equals A times x for some 4 by 4 matrix A. So in the invertible matrix theorem, that matrix A you see right here on par F, as well as in par I, is talking about the same matrix A mentioned right here on the very top of the theorem. Well, T is linear, so that means we can exhibit a matrix A. It's onto, so that means part I is true. Let's say that since T is onto, part I of the invertible matrix theorem is true. And so, well, we can now directly connect that with part A. A is automatically an invertible matrix. We're talking about that matrix A, the standard matrix for the transformation. And so A inverse exists by part A. At this point, we're done with the invertible matrix theorem. It doesn't give us any further information. But recall the prior theorem. Let's scroll up for just a moment. The prior theorem told us the moment you find that A is an invertible matrix, it means T is invertible, and so our job is done right at that step by theorem 9 of the current chapter. So down below here, this is something we could have put in the invertible matrix theorem, but to control the size of this, we're being choosy what goes in here. So it's not, say, a statement of 50 different concepts or something like that. We can now conclude T is invertible by theorem 9 of chapter 2. Only because of exhibiting that A inverse exists in the very first place. Well, any questions at all, folks? Working through example 5. It's kind of an unusual one because, again, this was just taking two parts of the invertible matrix theorem, connecting them, and then using another theorem that told us A inverse existing is synonymous with T being invertible. And example 6 might look funny, kind of looks like a typo, but if something like this were to happen on exam 3 or final exam, it's not a typo. It's written in the way, exactly the way it's meant to be. It says, assume that T from mapping R3 into R4 is linear. Explain why it's not invertible. You probably already are thinking the thought in the back of your mind. We were able to put down a square matrix when we exhibited the standard matrix through information of T being linear. If we do the same thing, we don't get a square matrix. We can now say, since T is linear, T of x equals AX, where A is, it's not 3 by 4, it's going to have to be of size 4 by 3. So reverse the domain and codomain dimensions. But even if I said 3 by 4, that's just a small mistake. It's not the critical thing. Critical thing here is that A inverse does not exist because A is not square. It has a different number of columns and rows, and that means we're done. Same theorem, theorem number 9. By theorem 9 of chapter 2, T inverse does not exist. Theorem 9 told us T inverse exists if and only if A inverse exists. That is logical equivalence. Much like all of these statements being logically equivalent, there's just loads of statements here. Anything that's connected by an if and only if means both concepts are simultaneously true, or both concepts are simultaneously false. Inverse non-existing means the inverse of the transformation doesn't exist as well. Well, that's the conclusion of the notes. If you want more practice with the invertible matrix theorem, I worked through all parts, A through M, on this example right down below. It's a lot of stuff to stare at, but if you want to see how all these parts connect with that specific one matrix, you can work through here where it's all going to be cranked out. But this is, again, pretty short section 2.3. We'll spend a little bit of time that we have left until about 3:45, just taking a preview into what's going on with determinants the moment the size is more than 2 by 2. We've already taken like a half a dozen determinants, like that right there is the determinant function. But you might have noticed we've completely avoided taking determinants of size 3 by 3. We'll see what the machinery looks like for that, as well as larger sizes. Any last questions or comments, folks, before we turn to the next chapter? Okay, I think the save took. So let's take a look into that next. So here's our introduction to determinants chapter. Here's where we're going to look into the basic machinery to taking a determinant that looks like this, of size n by n, where n can be 2, 3, 4, 5, maybe 50, and so on. The review topic is just for the sake of making the notes flow, but it's also the major idea is that there's a kind of recursion that goes on when we go to take a determinant. The determinant of a 3 by 3 matrix is defined in terms of determinants of 2 by 2 matrices. Likewise, the determinant of a 4 by 4 matrix is defined in terms of determinants of the 3 by 3 matrices, which are defined in terms of the 2 by 2 matrices. And it's in this sense, this determinant function that we're going to build, det for short, has a kind of combinatorial explosion in terms of the complexity in computation. There's an absolute limit. It's the limit of the processing power of our best machines out there, whether they're networked together or however they're configured, to the size of the determinant we can calculate based on these methods that we're going to see in the notes. So to start off how this kind of recursion goes, first we take the determinant of a 2 by 2, and this is what it looks like. We often wrote it this way, determinant A. We're thinking of the transformation. Det is just the name of a function, much like natural log or sine is also the name of a function. But the domain of the determinant function is kind of interesting. It takes a matrix and they have to be square. So it's of size n by n. So if I call det right here, the domain is going to be 2 by 2 for this particular determinant function. We don't put any different description here. We let the particular determinant function be read in through the context on what it's actually mapping. But the domain of this thing is R. And so in this sense, det is a scalar valued function. One thing that would be nice about this function that everyone would celebrate, and we would use and abuse this fact if it were true, is it would be awesome if the determinant function was linear. It's not linear. It fails on the additive equation. The determinant of one matrix plus another, you cannot separate as the determinant of one plus the determinant of the other. That's a formula that we don't have in fact. So let's say it right here. Determinant of A plus B is not the determinant of A plus the determinant of B, i.e., det is not linear, unfortunately. It gets another name. This is called a multilinear function because if we freeze one column, if we only operate on the determinant function by never changing this, we've reduced the size of the function. Now the only thing we're switching out is 5 by 1, or whatever vector goes inside there. It becomes this kind of function. So if you freeze one column, or all columns except for one, so the mapping looks like this, now it is linear. So in that sense, it becomes a multilinear function, but that becomes a pretty far concept from where we're at. That's a more advanced linear algebra topic. We're mostly discussing linear versus nonlinear. If you're curious on what would be a good counterexample, calculate out these things. A equals 1, 0, 0, 0. B equals 0, 0, 0, 1. If you work this out, it'll show that this determinant equation here breaks, and that's our counterexample, showing and proving that the determinant function is nonlinear. Still, it's an interesting function. It's scalar valued, it takes square matrices, and if the size is 2 by 2, it's a fast computation. We've done this a few times, but just for the sake of the notes, let's work through it carefully again. We take the product of the main diagonal, subtract the product of the off diagonal. This just looks like some weird numerical kind of game. But the moment you start to study this function more and more, even in our own chapter 3, this is a bizarre function, and it starts to give you the feel that the sense of function as a mathematical idea is just wildly, wildly vast, because this is one of the craziest functions ever. It's much like in calculus, where there are functions that are continuous everywhere and differentiable nowhere. This is a pretty remarkable function as well in that kind of sense. It's really unusual. And we'll see the ways it's unusual as well as we go through the notes. But for 2 by 2, this is all we do. 5 by 3 is negative 15. Minus 1, so we get a negative 16. And that's the first part of the definition, knowing how to compute a 2 by 2. Now we're going to up the size to 3 by 3 and see different methods for 3 by 3s as well. Any questions at the moment with just the initial topic? Okay, well, looking into how we're going to calculate larger size determinants, we need some machinery, and that's this notation here. So determinant A, when A is an n by n matrix, at size greater than or equal to 3, means our matrices are going to look like these. They have to be square. And that makes sense because the determinant function is part of the invertible matrix theorem, which is all about square matrices as well. So Aij is an arbitrary entry inside this matrix. We go to ANN, that's just the statement that's in the nth row and the nth column because it's a square matrix. Now here's how our new notation is going to work. A subscript ij is a kind of deletion. It's going to downsize our matrix to size n by 1 times n by 1. So if this started out as a 5 by 5, Aij is a 4 by 4 matrix. And what it does is it does a literal deletion of the ith row and jth column. We're going to be doing a lot of these because we'll relate a 3 by 3 determinant by deleting a certain column in a certain row to 2 by 2 determinants, just like this one. And that's how the recursion starts to work. So just for the sake of practicing those notations, here's what A13 would look like. A13 means delete row 1, delete column 3. And so now we have a 2 by 2 matrix, 3, 5, 1, 4. Does that make sense to folks on forming that notation there? Okay, digital ink is pretty convenient with this kind of stuff. Or you could use a pencil with really light strokes when you go to write these lines through, so you're not distracted by shadow lines. A22, this is also a size 2 by 2 matrix. The first 2 means delete row 2. The second 2 you see here means delete column 2. So it always starts with a row deletion, then a column deletion. And then we just write down the surviving entries. They go 2, 5, 4, 6. So that's the key ingredient in our notation. The next concept is going to be a so-called cofactor expansion. One thing that's really interesting about determinants I want to say before we look at that is determinants are a number game. It's kind of like row reduction, basically. Once you see how the pattern works, it's easy to understand how to compute the determinant. But what's actually a little bit trickier is how to write it down on paper what all those tricks by hand are really doing. Writing it down by paper is kind of clunky. But the book has to do it at some point, and this is what it looks like. We take a matrix with entries A, I, J, so we're thinking of that kind of matrix. The IJ cofactor we'll write down as a Cij. It's formed by deleting the ith row, the jth column, then taking the determinant, and then multiplying by either +1 or -1, where that positive negativity is determined by taking the power of the row plus the column on -1. So that gives you a cofactor, the IJ cofactor, and then the determinant of a matrix A. If we decide to do a cofactor expansion across the first row, that's row 1 right here, the zeros are kind of a welcome feature on this one, would have this format. Take entry A11, multiply it by the cofactor C11, entry A12, multiply by the next cofactor, and all the way down the line. We'll call that a cofactor expansion down row A. That's an interesting number game, so this is going to be our first practice of it. Let's maybe make this our last example of the day. We don't want to get too far on these notes on the last minute, since we'll be returning here after the exam, so back on Thursday. So here's our one to practice. Let's work through this carefully just to see what it's trying to say. So we're going this way. Cofactor expansion across row 1. We'll write out as det A for determinant of A. That means I'm thinking of that as my matrix A, but you can also write it this way: 0, 0, 2, 0, 5, 1, 1, 1, negative 3. It looks like you're writing down the matrix brackets, but you don't put in the hard edges. So make sure you don't put that in. We really mean a kind of absolute value bars. It's not absolute value in the sense that this is a positive constant. It can be negative, but there's some geometry there that somewhat relates to the absolute value function from the set of real numbers to the reals. So we copy that by putting absolute value in sense of that entire matrix. Now, first we take the A11 entry, that's 0. We multiply it on the C11 cofactor, which is going to be -1 to the power of ij. Well, this is row 1, column 1, so that's just going to be a 1 plus 1, multiplied by the determinant, aij. Well, that's found by deleting row 1 and column 1. So determinant aij is just this: 5, 1, 1, negative 3. And honestly, it looks silly writing this all down because we know 0 is going to multiply it. This is all just a glorified 0. But this is just for the sake of seeing the pattern as we write these out. So that's the very first term, this one. Oh, geez, can't delete it that way. Then we do it all over again. Go plus A12, row 1, column 2. That's the next entry, 0. Multiply it by the C12 cofactor, so that's -1 to the power 1 plus 2. Then we're deleting row 1 each time we delete row 1, but this time we delete column 2. Take the determinant of 0, 2, 1, negative 3. And one more term, I'll put it down here so we can fit it. One observation you might have noticed already is we're always deleting row 1 if we're doing a cofactor expansion across row 1. We deleted column 1, now we delete column 2, and next we'll delete column 3. And also, this is positive, this is negative, the next one will be positive. This is just an alternating sign. We're going to use and abuse that when we come back on Thursday. So this is what the full formula looks like and how to work with it. We'll also see what does it look like when you're just doing it by hand and not necessarily copying the formula steps verbatim. So the next step is go plus A1n. First, let me remove these marks. This would be A13 for us. So that would be row 1, column 3. The entry is 1. We multiply it by the 1, 3 cofactor. So that's going to be -1 to the power of 1 plus 3. Then we're deleting row 1, deleting column 3. Take the determinant of that submatrix, 0, 2, 5, 1. And now we've related the determinant of this to just 3 simpler determinants. This one is 0, this one is 0. We're just putting them down again to see the pattern. This is a +1 times a +1 times the determinant is going to be 0 on the main diagonal minus 10 on the off diagonal. So this whole thing is a glorified -10. Interesting in a way, it's a crazy number game. You might know this in how to do a determinant of a 3 by 3 in different ways. The interesting about this is that could have been a 4 by 4 matrix and the same work applies. These would have been 3 by 3 matrices, and we would have had to do another cofactor expansion across row 1 or maybe differently. And in that sense, it becomes a pretty big problem occasionally. The zeros here were a help for us this time. The other remarkable fact about determinants is the row isn't special. You can do a cofactor expansion across any row or any column, and the answer is always exactly the same. That's a weird fact about determinants already. The way these numbers go together and the way the determinant function actually operates means if you went down column 3, for example, it's a lot more work. You will get -10 guaranteed. So we'll explore that in a lot more detail when we come back next class. But any questions at all with our first 3 by 3 determinant? Okay, we'll come back to this next time. Have a great afternoon, folks. And if you have any questions as you're studying for the upcoming exam too, don't hesitate to reach out. I'll be extra available on the weekend, checking my email as well. But take care, and I'll see you all next time.
Could you go to example 5 on the previous section real
Yeah,
quick?
absolutely. Let me take a look at that.
I guess just a general question. How would I, because I'm looking at the exam like practice questions, how would I prove a linear transformation is nonlinear? Because I know that it would be like x x sub 2 minus 4 makes it nonlinear, but how would I prove that?
Oh, I see what you're saying. So to prove nonlinearity as an exam question, you've got to show that either t at, whoa, that was weird. Let me fix that real quick. We have to show that either t at u plus v is not equal to t at u plus t at v, or show that t at c times u is not equal to scalar c times t at u, or I think the other one you were mentioning was, or show t at the zero vector is not equal to the zero vector. So if this one fails, then this would be a good try right here. You might pick something like, say, c equals -1, u equals 1, 1, then take t at c times u, see what that comes out as, then take t of u, multiply it by c, see what this one comes out as. You're trying to go for, oh, the non-equal right there.
Oh, so with the c, you just pick one constant, or like whatever scalar you want, and just run through it and see if it works out.
Yeah, exactly. So if the transformation is something like this, t of x equals, maybe it's x1 plus x3. And let's say maybe for the next one, it's x1, x2. Then the multiplication right here is probably going to get messed up in some way by that -1 right there when we go to put in the
Okay,
c times u.
that makes more sense.
Awesome. Yeah, this would be a tricky one because there's, if it has t of x equals x1 plus 4 as just one single entry, like in the homework, then that just knocks the problem over immediately.
But like you couldn't say that because well, because like we defined linearity earlier by saying that you can't have an x sub 1 times an x sub 2. They have to be plus or minus.
Yeah, exactly. So that's kind of the same kind of concept of the system of linear equations required that same kind of thing. And that's the kind of same idea of what's breaking down right here at the same time.
Oh, okay. Thank you. That was about bothering me a little bit, but I
Gotcha. Yeah,
appreciate it.
glad to help with that.
Have a good one.
You too. Take care.